Hello, everyone. My name is Jose Martin Garcia, and I'm going to be talking with my colleagues, Jeff Bryan and Truman Tapia, on the new project, the Astro project that we are starting in version 13, and in which we will be continuously adding more material in new versions. So I hope we make this a new series of talks in the conferences to come. Okay. So in this talk, we are going to talk about three different things. Each of us will introduce one of these topics. In the first one, I am going to be talking about how we are improving our dates functionality to allow for the precise control of time needed in astronomical computation. And then Jeff will introduce some new Wolfram function repository functions dedicated to computation and visualization. And Truman will introduce some WFR functions related to how to get Astro data from external catalogs. So in version 13, we are adding a new option to date object. It's called time system, and it will allow us to specify the clock, the type of clock that has been used to measure that date. For example, in astronomy, this date is very important. It's called J2000. It's noon of the 1st of January of year 2000. And it's typically used in this time system, the terrestrial time system. We will explain in a moment what that is. So what we do now is that we have a new freedom in date object. You see it here. And together with the date list, the list of numbers, the granularity, the calendar, the time zone, we have now a fifth element, which is the time system, and we store there, TT. Once we have an object in a given time system, we can use time system convert to change the time system in the same way that we have calendar convert to change calendars or time zone convert to change time zones. And so, for example, we see that by changing to the standard civil UTC time system, we get a change of more than a minute. So for precise computation, it's very important to know in which of these two you are or any other one. And again, here we have UTC stored as an argument. So there is also, for example, TIE, the International Atomic Time. And we can also change and we get yet another number, etc. Those different date objects in different time systems, they all represent the same physical instant. It's just different representations. It's exactly like when you change one calendar to another calendar or one time zone to another time zone. Sorry. So, for example, if you have seen the previous talk when I was talking about the orientation data, if we compute what's the precision metrics at this instant, you see we get effectively numerical noise because this instant is the origin of those computations. However, if you confuse the time system and you ask for the same result in UTC, we get something which is small, but now it's not numerical error, certainly. So how many time systems do we have? We have of the order, we have 7 main ones. And here I give you notes. You can read these. Essentially, these are the ones that we are worried on Earth for civil purposes. These are the ones that are also related to Earth in astronomy. And these are other two that are used in astronomy when we are dealing with the time as seen from the sun or the solar system barycenter. There are relativistic corrections and there are shifts. For example, between this one and this one, we will see oscillations due to the speed of the Earth, etc. So if we change the value of now to the different 7 time systems, we get all these possible values. And as I said before, just by computing the distance between one and another in pairs, we get zeros because they are all the same instant. It's just different representations. For example, here we can see if we compute the difference of all these data lists in these two systems, this is time on the Earth, this is time for astronomy as seen from some correction from the sun, then we see an oscillation which during a year, which is due to the gravitational effects and speed relativistic effects of the Earth moving around the sun. And finally, I want to show how we deal with leap seconds, which is something that has been requested multiple times and we didn't do until now. So the thing is, we ask about what's the difference between these two. This is time, this is atomic time, this is UT1, this is solar time. As this is a time that follows the rotation of the Earth, this homogeneous rotation of the Earth that I was reporting before. And so we get that. Since the 60s, it has been changing. And you see, they were synchronized around 1958, I think, but now this is changing. And so if we shift this line by 0.9 seconds up and down, we get these two now. And if we now compute the difference between the atomic time and UTC, which is a shift by an integer number of seconds, at least now, we get this other curve. So this is the famous introductions of all these leap seconds that are introduced sometimes from time to time. So if we put the three things together, we see what's going on. We have the physical curve going here in the middle. We have the leap second curve approximating it. And the definition is that the red curve can never touch the two observed blue curves. And see, this is how it's decided whether to add one or another one. And see how it's very interesting, because the Earth is speeding up recently. It might happen if it goes down far enough that we have to remove a leap second at some point in the next few years. And for example, if we have all these half seconds, you see they are all continuous, and we change from tie 35, 5, 36, 36, 5, etc. to UTC, then the object knows now that there is 60 and there is a 60.5 and then 0, right? So this is this is a moment that existed during a leap second. So that's something that the UTC system knows. Okay, so those were my 8 minutes dedicated to time improvements. And now I'm going to let Jeff continue talking about WFR functions. Jeff?
All right. Thank you, Jose. Give me a second to share my screen here. So one of the things I work on is mainly on the alpha side, and alpha has a lot more of the kind of more domain specific astronomy type functionality. We're just now getting going on incorporating that into the kernel as shown by Jose. But on the alpha side for a while now, we've had a lot of specific astronomy functionality, and we wanted to make sure that that was at least available to the Wolfram language. And the way that we do that, if we don't already have a built-in function that does what we do on alpha, we can write these Wolfram function repository items to essentially expose usually the same. Sometimes it's an improved version of what you see on the alpha website. So what I've worked on here recently in the last few months actually has been to try to create as many of these as possible to expose the astronomy functionality that we have there. So here you can see some kind of the Wolfram language forms of some of these Wolfram function repository items. And you can see here that, we've got a way of essentially viewing Jupiter from the Earth, so you can see where the great red spot is. It may or may not be visible at a given time instant, but I've chosen a time here where you can see the great red spot is visible, so you can see it'll show up right here. And so if you were to go out with a telescope and look at this time, you would have seen the great red spot there. Each of these, of course, has their own reference page, so you can actually click on documentation and go see all the options that are often available for those. We have another one for viewing Saturn in 3D. So this is actually shows the correct tilt of Saturn's rings as seen from Earth. So you can give that different dates and see how the inclination of Saturn's rings changes as observed from the point of view of Earth. We've got a fairly recent one here. We got a lot of requests for people wanting to know various different types of twilight, morning astronomical, evening astronomical, and all the variations of that. So we've now got a twilight times function repository item that will give you an association, or you can ask for any one of them individually. We have a graphic kind of like this on the Alpha website, but it's 2D. So this version here is a little bit nicer. It's 3D, but it gives you kind of an orientation showing where the Earth, Moon, and Sun are with respect to each other. The Sun, at least the direction of the Sun, is shown by the arrows here on the left. This is actually something you can actually rotate if you have this on your local system. So, but by default, it's viewed from above the plane. Then, of course, we have the constellation chart here that kind of shows you for a given constellation entity, what that constellation looks like, where its boundary is, and some of the bright stars are highlighted with callouts. Now, that's fine if you can remember what the input form is, but one of the other things that we have is Wolfram Alpha Notebook Edition now. Wolfram Alpha Notebook Edition is based entirely on natural language. So if you can't remember the input form for some of these new functions, you can just use natural language. And so here's basically the same things that I was just showing you, but using control equals if you're in a regular Mathematica notebook, or if you're in a Wolfram Alpha Notebook Edition notebook, you've already got an input field presented to you, and you can just type in queries like configuration of the Galilean satellites. And if you go in here and then you kind of exit, you will see that it will resolve into the Wolfram language form, and then you can then edit it, add options, anything like that that you would like. And then you evaluate it, and it'll actually update. So this gives you the current configuration of the Galilean moons of Jupiter as seen from Earth. Same thing with the Great Red Spot. Here you've got an input that actually generates the input form that you can then edit. Orientation of Saturn's rings, a natural language form there. And same thing here, Earth, Sun, Moon configuration. It doesn't just apply to things that are in the Wolfram Function Repository. A lot of these natural language things, especially with Wolfram Alpha Notebook Edition, we can use that to translate into things that are built into the system. So for example, since this is kind of astronomy related, we actually have the ability to query for relief maps of Mars. This is using geo-elevation data. We've got texture maps for many of the solid bodies, most of the solid bodies in this solar system that have actually had pictures taken of them. So here you can see the moon Io around Jupiter, and we can show one of the volcanoes, Pele, and where it's located here. And then orthographic map of the moon. So just some examples of some of the things we've exposed through that mechanism. I'm going to turn this over at this point to Truman, and let me stop my video.
Thank you, Jeff. Okay, I am going to present several functions in the Workframe Repository. Function that get information from several astronomical databases. The first function is called Simbad identifiers. Well, Simbad is a database with more than 12 million astronomical objects, and the function Simbad identifiers returns all the identifiers or alternate names for a given astronomical object. For example, you can call the function for an entity astronomical object, for example, Altair, in this case, and you get a list of all the identifiers, in this case, 61 identifiers. A more general case is the function Simbad data, which extracts basic information from Simbad for astronomical objects. One can think of this function as an extension of the Wolfram knowledge database. And we can use it passing an object as first argument, and the second argument just calling the properties that we want to retrieve. As you can see here, and we can specify an object by entities or by strings. To take a look on the available properties, you can run this code offline. But also, as I mentioned, Simbad has 12 million objects. So we can serve this amount of data by providing sky regions instead of object names. For example, here I am specifying a circle in the sky centered at Sagittarius A star, and with a radius of 0.5 arc seconds. And we get these properties from the objects that lie inside this circle, and we get the result as a data set. So these are the list of the objects that are close to the black hole of the Milky Way. The function VCR catalog data gets catalogs from VCR. VCR is a library with more than 20,000 astronomical catalogs. And a typical use, we will use the first argument as a keyword. So we look for all the catalogs that match with Hipparcos keyword, and we want the title property from these catalogs. And we get an association with keys as the catalog IDs, and the values are the titles. In this output, we can see, for example, in the first case, we see that this is the catalog ID of the main Hipparcos catalog, and we can get the catalog, some rows of the catalog, by specifying the table ID as the keyword. But also, because some catalogs in VCR are very large, we can search information inside the catalog. For example, here we get the Hipparcos number of Nenke, and then we ask for the information of this star inside the Hipparcos catalog, and applying a filter. And just to mention that VCR has new and large catalogs. For example, the Gaia early data release was published in the last year, and it has 1.8 billion objects. And this is how you get the size of the catalog, and this is the idea of this catalog. And you can get rows, as always, as using the table ID. Finally, I want to talk about the new function SkyViewImage, which retrieves images from SkyView. SkyView is a virtual observatory generating images of any part of the sky at wavelengths in all regimes, from radio to gamma rays. For example, we can get an image of a galaxy, the galaxy M87, just passing the entity. Also, we can get fit images, specifying the second argument, in this case of the star Altair. And we use the second argument as we will use in the import function. And here you can see another example of the galaxy M88. And this image is extracted from the Sloan Digital Sky Survey V-band data release 7. In conclusion, we can now specify and change time systems in dates for precise control of time. Also, we have seen examples of the use of a variety of astro-related WFR functions, both for computation and visualization. And also, we see WFR functions to connect to large astro catalogs and databases. In the future work, we plan to introduce astroposition, following geoposition to change coordinates and frames in astrometry. Also, we plan to connect with SPICE kernels to get precise data about the solar system objects. And also, we plan to introduce astrographics, following geographics to produce star maps and views of the sky. Thank you for attending this presentation. And I think we are open to questions.
Thanks, Truman.
Okay, let's have a look at the questions in the chat.
The presentation notebook, Jose, have you uploaded that yet?
Yes, I did.
Okay, so it should be available through Pathable then.
Mm-hmm.
Okay.
Also, if you do not see it in Pathable, please refresh your page.
Let's see, we have a question from Jesse. Is there a roadmap towards local computation of time series of positions of solar system objects. Yes. So we are building a library link connection to this great library that NASA and JPL have called SPICE. And this is able to read their kernel files where they have very precise data for planets and satellites, even spacecrafts. These kernel files also have information about the clocks of the spacecraft, the orientation of the spacecraft. So yeah, we will connect to that, and that will provide the information you are asking about.
Yeah, Dave DeBroda's question just before that is similar. We expect that once we have SPICE and things like that, it should be able to allow us to view, what does Mars look like from the observation point of, the Mars Reconnaissance Orbiter, things like that. Can it project locations of named comets? We have Solar System Plot 3D, which is a Wolfram Function Repository item. And if you use that WFR and you feed it in the entity that represents the comet you're interested in, it will generate a graphic showing you the orbit of that comet and its location. It also allows you to feed in dates so you can see that with time. So that kind of stuff isn't yet available in the Wolfram language directly, but we do have WFRs that can do that kind of thing. I think I saw somebody ask a question earlier about whether light time was taken into account. I think this had to do with probably the Great Red Spot, I'm guessing, when I was showing the Great Red Spot. And basically that's the view that should be visible in your telescope. Now, the one thing you have to keep in mind with the Great Red Spot is that it moves with time. And because it's a weather system, it does not move in a predictable manner. And so from time to time, we have to manually update the longitude of the Great Red Spot of Jupiter so that our computations are correct. So right now, I think it's probably a little bit off because I haven't updated it in a while. So if you were to actually compare what we give you to what you actually see through a telescope, you're going to see a longitude shift there a little bit because the Great Red Spot's not technically quite in the right position. So, but once I update that, it should be pretty close to what you would see through a telescope. So I think by that, you mean, yes, that takes light travel time into account because it's showing you what you should see, through your telescope. Because Jupiter's, I'm trying to remember how far Jupiter is. It's
there is a question from Thomas saying that asking about how to use NASA's data.
I think that's the ephemeris that you're referring to.
Yes, exactly. So yes, we are planning to provide an interface to that, and we will try to, as usual, as we always do in Wolfram language, to make it as simple as possible, that you don't have to worry about the internal details of how this works. It should be all high-level interaction.
Once again, we remember for after version 13, it'll probably be in 13.1, we plan to have SPICE built in. Once that's there, you should, in theory, have some mechanism, which we haven't yet actually put together, but you should be able to obtain any JPL ephemeris file that you want to use, and hopefully drop it in or point to it and be able to talk directly with Wolfram language using that. There's lots of them. Some of them are quite large. I mean, just for the solar system alone, just for the planets, the sun and the moon, that one is like 10 gigabytes. And so we haven't yet decided how we're going to provide that so that you get really precise positions of the planets, but probably it'll be an optional download or something like that, where you just drop it, put it in the right location, and SPICE that's in Mathematica will just talk to it. But those are details that have yet to be worked out, but we do have plans of tackling it.
Mm-hmm. Jesse is asking about span of time. So this doesn't go millions of years, but it does go thousands of years.
Right. I don't think anybody, I mean, NASA does the best job that you can. And I mean, they take crazy things into account, including the offset of the moon's core, I think, from its center when they're computing, the perturbations that go into a account of computing everything, including the non-sphericity of Jupiter. On how it pulls on ground. So it does the best you can do with long-term computations, but nobody can go out accurately millions of years. thousands of years, yes, at least out to about, say, 3,000 years. I don't remember how far they can push it out for like the JPL 431. I think that's the most recent one, but probably 3,000 years at least. You go beyond that and you're basically extrapolating. The errors build up over such long periods to the point where it becomes harder to say for sure what the perturbations were.
John Snyder is asking whether we already have something in WFR to connect to that, and we don't. This will be done via library link connection.
Right.
For speed.
Yeah, Spice and everything like that is pretty much done at the C level, so it's kind of hard to do that at top level without library link. Okay, Christopher Wolfram said that the DE 441 goes back to 13,000 BC. I haven't looked up the 441 to know what that covers. Is that the planets and the moon, or is that some subset? You have to be careful. JPL provides so many of these DE sets that they all do different things. Some are specific to individual spacecraft. Some of them are for, just the moons around one planet. It's, lots of different ones. Interesting. I knew the 431 was out. I didn't know a 441 existed, but they're getting quite large. I think the 431 was 10 gigabytes in size. So obviously we can't drop that into the Wolfram language and ship with it. That's a bit too big. I don't think people would appreciate bloating Mathematica by 10 gigabytes just to do that. But we do have some data on proper motion and Hipparcos and that kind of stuff already. At least that's through entity value. However, we probably, in whatever endeavors we do for astronomy moving forward, won't rely directly on getting data from entity value directly. I think it's just slow for the sheer amount of data we need to get quickly. So, we're going to have to explore faster ways of getting batches of data, perhaps even tiled data, similar to the way they're doing things with the new vector maps for geographics. They deliver, essentially that's vector data. We may do the same thing for astronomy data. We don't know. We're going to have to look at our technologies and see what can be leveraged. But I think if you try to request thousands of stars very quickly to generate a star chart and you have to wait many minutes to get it down, it's going to be kind of a painful process. So that's one of the things we have to solve.
There's a question here, which I think is for Truman, about whether the images we download have meta information and astrometric positions. Do you know, Truman?
I think you're referring to the images of Escape View.
Mm-hmm. Is there any sort of meta information there?
Let's see. Generally, when they provide fits file, they should. But I am not sure about it. I haven't tried it. Well, the default gets an image, but I am not sure, to be honest.
Okay.
Christopher's talking about Hipparcos proper motions again. Hipparcos is actually somewhat obsolete. The new Gaia mission is getting far more precise proper motion data for a much larger collection of stars, something like 1 billion stars. Unfortunately, the modern satellites collect so much data, it's actually unwieldy. It's hard to deal with. Hipparcos is dated about 1991. And yes, it did have values, and I think we have most of that data already in entity value. And also Truman showed he has VisiR data. You can actually get the entire Hipparcos catalog from his VisiR data interface here, and that's in the Wolfram function repository. So if you just want the raw data, you can get it that way. If you wanted to align to entities, you can try doing it through entity value, but that data didn't just come from Hipparcos. It's probably a mixed bag because Hipparcos didn't see everything. It had a limited magnitude range and things like that. So. We'd love to have more Gaia data. It's very precise but huge, but cross-referencing is a problem in the sheer size of the amount of data. It's easy to systematically examine a lot of stars, but then to cross-reference them with every other catalog that's ever existed to know which data point goes with which star that you already know a different name for takes a lot longer to get it in.
Coming
Okay.
back to the last question, I think that this is, for example, the type of metadata, but it's not
Great.
a lot.
Okay, well, I think we are running out of time. There's one more question here from John asking about the time system UT2. That is not so used. Yes, there is UT0 and UT2. They are not so much used recently, so they were not added, but they could. It just yeah, I just said corrected versions of UT2, UT1. Okay, any final? One more question for Truman. Do the databases store light curves? Is there such information there?
I don't
I
think
think that
VCR does.
well, VCR is actually pretty big. So usually people, when they publish the papers, they tend to publish their database their data there. So you can take a look, but I don't have that table ID right now to say this is what you're looking for.
Right, you probably have to look on it, and not every catalog out there has light curves, so you'd have to specifically look in VCR to see if there's a catalog that includes that data. So it might. I guess that's a short answer, right? I know that the AAVSO, if you're interested in light curves, especially for stars, American Association of Variable Star Observers, AAVSO, they actually have a very large collection of light curves for stars. We don't have a direct interface to that, but I believe they allow you to query for the data that you want and download it. I don't think they have an API. I haven't looked in a while, but I know I've plotted that kind of data before, if that's the kind of light curves you're looking for, but it's limited to stars.
You have in the notebook the link to VCR if you want to take a look.
Right.
Okay, so thank you very much for attending this talk. And if you have comments, suggestions, this project is starting, so we will be very happy to know about them. Thank you very much.